Hello, and welcome to a new edition of H.E.L Explains with your host, Dr. Mario Toubes-Rodrigo. And today, we are going to be talking about thermal runaways and why we should care about them. There is a very high chance that you're watching this video using either a laptop or using a mobile device. Also, it's going to be very likely that these devices are being powered by lithium-ion batteries. And one only needs to look at the news to see that lithium-ion batteries are becoming quite trendy. And let's see why. Thermal runaways are linked to reactions. And let's imagine that we have a very simple one, so A plus B to produce C and D. And it can behave in one of two ways, as we have discussed a number of times. It can be the case that it absorbs energy in an endothermic kind of regime, or it can produce energy. The problem with this energy being released is that it can increase the temperature in the surroundings of the chemical reaction. And if that's the case, we can get trapped on a feedback loop in which the heat that is being produced in the chemical reaction is going to even increase the speed, the rate at which reaction happens in a positive feedback loop. And if we analyze how the temperature increases in this case, we're going to see something like the graph that I've just shown. So we can see that the temperature is going to increase steadily, but then it's going to reach a point in which there's going to be a massive acceleration, which is what we can see in the middle of the graph, and this is what we call a thermal runaway. So, what is it about lithium-ion batteries that make them so prominent in the press? Well, the first thing is just the sheer amount of them. Between 95 and 99% of all the rechargeable batteries around us are lithium-ion batteries. But these batteries are not that different from the rest of the batteries. They also contain a cathode, an anode, an electrolyte, and to make them even safer, most of them also contain a separator. The issue is that some of the components in the batteries are susceptible to decomposition reactions. For example, the electrolyte, that normally is an organic carbonate, can break down in a decomposition reaction, generating an organic gas, hydrogen, and CO2. And these batteries, when there is this decomposition reaction, swell and they look something like this. But also, the cathode can be exposed to high temperatures because of the first decomposition reaction, and it's also susceptible to decomposition. And in this case, the lithium metal oxide can break down, generating oxygen, lithium, and the metal. So now we have a combination of high temperature, an organic gas, and oxygen, and this is a very dangerous scenario. Well, we have seen that lithium-ion batteries are not perfect. They have their issues. And we can use certain tools to test them and to try to make them safer. One of them is the use of calorimetry, and different types of calorimetry are going to help us understand how the battery is going to behave in normal testing conditions, but also we can test them for the worst case scenario. So let's dig into it and let's see what this is all about. The first type of calorimetry I want to talk about is isothermal calorimetry. And in this case, the calorimeter, the device that we use, is going to be equipped with a heater. So for example, we have the ISO-BTC manufactured by H.E.L. In this case, the heater is going to make sure that the battery is operating at a stable temperature. And then we can analyze how the battery behaves in this case. So for example, at 40 degrees and 60 degrees, that's the pink line that we have on the graph on the right hand side of this slide, we can see that the charge process becomes a peak and the discharge process is a trough. That means that the charging process is an endothermic process, so the heater will have to supply extra energy, that's what we can see in blue, whereas on the discharge it has to pull back because it's an exothermic process. However, this situation changes at lower temperatures, and in this case both the charge and the discharge become a trough, which means that both of them are going to become endothermic. So we will have to think about this when we are operating our batteries, because it means that we'll have to supply extra energy at the time of charging it, and it's going to be less efficient when discharging. The second type of calorimetry I want to talk about is adiabatic calorimetry. And this is the one we use to test for the worst case scenario. What would happen if the battery goes into a thermal runaway? So we have approaches such as heat, wait, surge, in which we are going to slowly warm and heat up our battery, and we are going to let it wait and see how it behaves in this new temperature. The objective of this is testing for an exotherm, testing for the temperature in which the battery is going to go into this process of thermal runaway. And this is what we can see on the graph we have on this slide. We can see that every single step, the battery stabilizes at that temperature. But when we reach around 120 degrees, we're going to have a huge exotherm. We're going to find that the battery is going to start self-heating and is going to increase from 120 degrees up to over 350 degrees. This is what a thermal runaway looks like. But we can also do this kind of testing and make the battery fail using other approaches, such as, for example, puncturing it or smashing it or crashing it. This is where calorimetry, and especially adiabatic calorimetry, just shines through. I have talked about how we can use calorimetry to analyze how the battery can fail so we don't get into those conditions. But it can be the case that the environmental conditions are going to change, or the battery is going to be exposed to some kind of physical damage that is going to make it go into thermal runaway. It is in this case when we need to have extra measures that are going to stop the thermal runaway and is going to try to make the situation not going any worse. One of them is, for example, the use of separators. And I've briefly mentioned separators when I was talking about this physical structure of the battery. Separators are physical barriers that are going to allow the movement of lithium ions. However, when the thermal runaway happens, the physical structure of these separators can change. It can be, for example, a polymer, and polymers can react to high temperatures, collapsing, preventing the pores inside of the polymer structure to allow the free movement of lithium ions, and therefore they're going to stop the chemical reaction. But also, in last few years, there's been some research into trying to use some other electrolytes that are not liquid and that they are not susceptible to thermal runaways and decomposition. And one of them is the use of solid state batteries. In this case, we're going to use something like a ceramic or some chemical structure that is solid that is going to allow the movement of the lithium ions, but because of the chemical nature of this solid state electrolyte, they're not going to decompose. So the take-home messages I want you to take from this video today is that understanding and preventing thermal runaways in batteries is critical, especially because nowadays we are shifting towards electrification, and with this electrification there is a pressuring need to increase the storage of energy in our batteries, make them even potentially more dangerous if they go into thermal runaway. Also, that we need rigorous testing procedures, especially calorimetry, because calorimetry is a very powerful tool for this. So with this kind of testing, we can understand where the thermal runaway triggers, such as high temperature or physical damage. And finally, that research and innovation are also fundamental to build safer batteries. We have seen things such as separators or solid-state batteries that can really help to solve this situation. And that's it. That's from me. My name is Dr. Mario Toubes-Rodrigo, and I'm the applications leader at H.E.L. So please, if you have any questions, if you have any comments, please come and talk to us. Thank you very much.